You're listening to Scientific Giants Who Changed the World. Each episode stands beside one mind and follows a thread of curiosity until it ties to the world we inhabit. Today, we meet a man who understood, earlier than most, that the crisis in physics was not just a technical crisis. It was a crisis of language. It was a crisis of what we mean when we say we describe reality. His name is Niels Bohr. And if Max Planck opened the door to the quantum world with a reluctant step, Bohr walked through that door and began furnishing the room. He did it with a mixture that is almost never found in one person: mathematical seriousness, experimental respect, institutional ambition, and a philosophical instinct for where words break. Bohr was born in Copenhagen in 1885, into a home where thought was not a hobby, but an atmosphere. His father, Christian Bohr, was a physiologist. His mother, Ellen Adler Bohr, came from a cultured and influential Jewish family. The house was full of conversation, argument, and books. Bohr and his younger brother Harold, who would become a notable mathematician, grew up in a Denmark that valued education and civic life. And they grew up with a kind of confidence that comes from being treated as capable from the start. Yet Bohr was not an effortless prodigy in the mythic sense. He became a giant through persistence and an unusual sensitivity to contradictions. As a young man, he studied at the University of Copenhagen and began with work that looked safely classical. One early project involved the surface tension of water, a subject that can feel mundane until you remember that physics often begins with the mundane and then reveals its depth. But Bohr's mind was already turning toward the atom, toward the question of what matter really is and why it behaves as it does. By the time Bohr entered the wider European physics community, the atom was in a peculiar state. It had become, for many scientists, not just a philosophical idea, but an experimental object. J.J. Thomson had discovered the electron in 1897, proving that atoms contain smaller charged parts. Thomson proposed a plum pudding model: electrons embedded in a diffuse positive charge. It was a picture, and like many pictures, it helped for a while. Then Ernest Rutherford, working with Hans Geiger and Ernest Marsden, performed the famous gold foil experiment. They fired alpha particles at thin metal foil and found that most passed through, but a small fraction scattered at large angles, as if they had hit something hard and concentrated. Rutherford interpreted this as evidence that the atom has a tiny, dense, positively charged nucleus, with electrons somehow around it. This was an astonishing conceptual leap. The atom was mostly empty space, yet stable. The nucleus was a speck compared to the overall atom, yet it held the structure together. Bohr went to England and worked with Rutherford in Manchester. The meeting between those two minds matters. Rutherford was a force of nature, direct, experimental, energetic, sometimes impatient with excessive theorizing. Bohr was quieter, more reflective, drawn to the places where theory and observation failed to meet. He admired Rutherford deeply, and Rutherford recognized Bohr's intellect even when he found Bohr's style too slow. Now, here's the problem that haunted them. If you take Rutherford's nuclear atom and apply classical physics, it cannot exist. An electron orbiting a nucleus is an accelerating charged particle, and classical electromagnetism says an accelerating charge radiates energy. If the electron radiates energy, it loses energy. If it loses energy, it spirals inward and collapses into the nucleus. The atom should be unstable, collapsing in an instant. Yet atoms are stable. Matter persists. Tables do not dissolve. Life does not fall into its own nuclei. Classical physics, at the heart of the atom, was predicting that the world should not be here. This was not a small technical mismatch. This was a contradiction between the theory that had built the 19th century and the stubborn fact of existence. At the same time, there was another pressure. Atoms emit and absorb light in very specific colors, specific frequencies. Spectroscopy, splitting light from elements into lines, had become an extraordinarily precise tool. Each element had a fingerprint of spectral lines. Hydrogen, the simplest atom, had a spectral pattern that had been summarized in a formula by Johann Balmer and later generalized. There was an order there, a hidden arithmetic. But classical physics did not explain why atoms emit discrete lines instead of a continuous smear. Bohr saw these two problems as one problem. The stability of the atom and the discreteness of spectra were not separate puzzles. They were two faces of the same deeper truth. Something about energy and atoms is quantized. In 1913, Bohr proposed his model of the hydrogen atom. The word model is important. Bohr did not claim he was describing the full truth of atomic reality. He was building a structure that could hold the data without collapsing into contradiction. He took Rutherford's nucleus seriously. He took Planck's quantum idea seriously. He took the spectral data seriously. And then he did something both daring and carefully limited. He imposed quantization rules on the electron's motion. Bohr proposed that electrons can orbit the nucleus only in certain allowed orbits, and that while in these orbits they do not radiate energy, despite being accelerating charges. This alone was an open violation of classical electrodynamics, and Bohr knew it. He did not attempt to justify it with a classical mechanism. He simply declared that the atom obeys different rules, and those rules include stationary states, where the electron is stable. Then he introduced a rule for radiation. Light is emitted or absorbed when an electron jumps between these allowed orbits. The frequency of the emitted light is determined by the difference in energy between the initial and final states, divided by Planck's constant. Suddenly, the spectral lines, those discrete fingerprints, were no longer arbitrary. They were the result of discrete energy levels and quantum jumps. Bohr also imposed a quantization condition on the electron's angular momentum. It must be an integer multiple of a fundamental unit related to Planck's constant. That condition, combined with Coulomb's law for attraction between electron and nucleus, yields a set of allowed radii and energies for the orbits. And the resulting energy differences match the observed spectral lines of hydrogen with striking accuracy. It is difficult to convey how explosive this was, because the result arrived as a kind of peace treaty between the old physics and the new. Bohr's atom used classical orbits, an image people could still visualize, but it inserted quantum rules that made those orbits discrete and stable. It was neither fully classical nor fully quantum in the later sense. It was a bridge, and bridges are often built before the land on either side is fully mapped. Bohr's model was immediately successful for hydrogen and hydrogen-like ions, and it gave physics something it desperately needed: a concrete framework that connected quantum ideas to real atomic behavior. Yet Bohr was not fooled by his own success. He knew the model was incomplete. It could not easily handle more complex atoms. It relied on postulates that felt arbitrary. It treated electron orbits as if they were real paths. But the deeper implications of quantum theory were already pressing toward a different notion of what an electron is. Bohr's greatest contribution might not be the orbits at all. It might be the way he taught physics to live with paradox without becoming incoherent. To understand that, you have to see what Bohr built next. He returned to Denmark and became not only a theorist, but a builder of institutions. In 1921, he founded what became the Institute for Theoretical Physics in Copenhagen, later known as the Niels Bohr Institute. This was not just an academic department, it was a new kind of place, an international workshop where young physicists could argue, collaborate, and test ideas in real time. Bohr created an environment where disagreement was not a threat, but a tool. And people came. They came because Bohr had become a center of gravity in the quantum world. He had a reputation for deep, patient thinking, for listening carefully, for asking questions that sounded simple, but went straight into the heart of a problem. He also had an unusual personal style. He was not a sharp debater, in the sense of quick rhetorical victories. He was slow, often hesitant in speech, sometimes painfully searching for the right phrasing. But his slowness was a form of honesty. He would not pretend clarity when clarity had not been earned. In the 1920s, quantum theory entered a period of rapid transformation. Bohr's old quantum model with discrete orbits began to be replaced by something more abstract and more powerful. Werner Heisenberg developed matrix mechanics. Erwin Schrödinger developed wave mechanics. Max Born clarified probabilistic interpretation, and Paul Dirac unified frameworks with stunning mathematical elegance. The old quantum theory of quantized orbits was giving way to quantum mechanics proper. Bohr was not merely watching, he was shaping the interpretive ground on which this new physics would stand. Bohr introduced and defended what came to be called the Copenhagen interpretation, though the label can be misleading because it suggests a single fixed doctrine. Bohr's own view was subtle and sometimes frustratingly difficult to summarize. One is complementarity. Bohr argued that quantum phenomena require mutually exclusive but jointly necessary descriptions. Light, for example, can behave like a wave in interference experiments and like a particle in photoelectric effects. These are not just two opinions about the same underlying classical object. They are two complementary ways of describing behavior that cannot be captured in one classical picture at once. The experimental setup determines which aspect is manifested. You cannot simultaneously observe all classical attributes because the act of measurement is part of the phenomenon. This was not merely an epistemological statement, we don't know everything. It was a claim about what it means to describe nature. Bohr insisted that physics is not a window into an independent reality described in a language detached from experiment. Physics is an account of what can be said about nature given the conditions of measurement. The measuring apparatus is not an external spectator. It is part of the situation. In the quantum realm, the division between object and instrument is not cleaned. This is where Bohr's philosophy becomes essential. He believed classical concepts, position, momentum, time, energy, are indispensable because they are embedded in how we communicate experiments. We need classical language to describe the apparatus and the outcomes. Yet the quantum world does not always permit those classical concepts to apply simultaneously with full meaning. So we use classical concepts, but we accept limits on their combined application. That is complementarity, not a shrug, but a structured discipline of description. Another theme is the correspondence principle, which Bohr used even before full quantum mechanics. It states roughly that quantum theory must reproduce classical results in the limit of large quantum numbers or large scales. This principle served as a guide during the messy transition period, helping physicists ensure the new theory did not lose contact with the old, where the old works well. Bohr believed revolutions in physics should not destroy success. They should explain why success was possible. Bohr also became, in the eyes of many, the conscience of interpretation. When brilliant younger physicists produced mathematical formalism, Bohr asked, "What does it mean? What can we say the theory claims about the world?" When debates became too metaphysical, Bohr pulled them back toward the structure of experiment. When debates became too instrumental, Bohr pushed them toward philosophical clarity. He was, in that sense, an architect not only of a model, but of a style of thinking. His relationship with Einstein illustrates this. Einstein accepted quantum mechanics as a set of predictive rules, but he resisted its implications about indeterminacy and the role of measurement. In various forms, that God does not play dice. Bohr replied, in effect, that we should not tell God what to do. But the real content of their debate was deeper. Einstein believed a complete physical theory should describe an objective reality independent of observation. Bohr believed quantum theory shows that the conditions of observation are woven into the description. Their debates, especially at the Solvay conferences, were not mere intellectual theater. They were the struggle to decide what science is allowed to claim. Bohr's own stance was sometimes criticized as evasive, as if he were hiding behind language. But if you listen carefully, his position is not a retreat. It is an attempt to respect what the theory and experiments actually force us to confront. In the quantum world, you cannot talk about the properties of a system as if they exist with definite values independent of measurement contexts, at least not in the naive classical sense. Bohr's interpretive framework insists we keep our claims tied to possible experimental arrangements. It is a discipline, not a surrender. Then there is the political and human dimension of Bohr's life, which cannot be separated from the 20th century. During World War II, Denmark was occupied by Nazi Germany. Bohr, with his Jewish maternal heritage, was at risk. In 1943, he escaped Denmark in a dramatic flight to Sweden and then to Britain and the United States. He became involved, reluctantly but seriously, with the Allied atomic bomb project, the Manhattan Project. His involvement was shaped by a vision that can sound naive but was morally urgent. He believed the existence of nuclear weapons would force a new kind of openness among nations, a transparency about scientific capabilities that could reduce the risk of catastrophic secrecy and arms races. Bohr tried to persuade leaders, including Churchill and Roosevelt, that the post-war world would need international cooperation and openness about nuclear technology. He argued that secrecy would create suspicion and accelerate conflict. He saw with painful clarity that scientific knowledge cannot be unlearned, and that the weapon had changed the political structure of human existence. History did not follow Bohr's hopes. The Cold War emerged, secrecy deepened, and arms races escalated. But Bohr's warning is not wrong. It was ignored. He spent much of his later life advocating for peaceful uses of atomic energy and for international cooperation. He received the first Atoms for Peace Award and continued to be a moral voice in science. Yet Bohr was not simply a moral symbol. He remained at core a physicist who believed that the hardest part of the quantum revolution was not the math, but the meaning. He knew that people could write equations and build devices without fully digesting what they imply. He knew that language becomes a battlefield when nature refuses to fit our categories. So how should we remember Bohr? We should remember him as the man who made the atoms speak. Before Bohr, atomic spectra were patterns without a story. After Bohr, they were evidence of discrete structure. We should remember him as the builder of Copenhagen, not merely a city, but a school of thought, a place where quantum theory became a living conversation. We should remember him as the architect of complementarity, the one who taught physics that sometimes the world demands two incompatible pictures, and the price of truth is accepting that you cannot fuse them into one classical image without losing something real. We should remember him as the mentor and interlocutor, the one who could sit with the sharpest minds of the era and ask the slow questions that revealed hidden assumptions. If you want a final image, picture Bohr in a room filled with young physicists, chalk dust in the air, arguments in motion, and Bohr, hesitant, searching, trying to find the precise phrasing that will keep everyone honest. Because in the quantum world, honesty is not only about data, it is about refusing to say more than the experiment allows, and refusing to say less than the theory demands. You have been listening to Scientific Giants Who Changed the World. Today, we followed Niels Bohr from the stability problem of the atom to the conceptual foundations of quantum mechanics, from quantized orbits to complementarity, from Copenhagen's Institute to the moral storm of the nuclear age. In our next episode, we will meet Werner Heisenberg, who discovered a new mechanics in a burst of intense work and then articulated a principle that sits like a knife edge at the heart of nature: uncertainty. Until then, thank you for your attention and your time. This episode was written as a continuous story for the ear, because ideas like complementarity cannot be absorbed as slogans. They have to be lived through step by step, until you feel where language breaks and where a new discipline of description begins.